Welcome to the survival time analysis tutorial. So survival time analysis or survival time analyses are actually a suite of methods to analyze survival or occurrence data. And so in our case, we're going to be looking at survival data. More specifically, the example is survival data of roaches exposed to different temperature treatments. But the event is essentially we're a suite of methods used to look at the time to an event. And while death is certainly one of the more common ones that's used, we can use other events, right? So this is a very popular suite of techniques in biomedical sciences where we look at time to relapse or survivorship after diagnosed with a disease, right? And so there's multiple questions we can ask, but we're essentially looking at what factors might contribute to the time of some event, whether it's relapse or death or some other event we want to measure. So it doesn't have to be survival, but again, that's the most common. Okay? And so again, what we really have here is we've got our samples, our individuals that we track through time, and we can have a series of explanatory variables about our individuals. We can know their sex, we can know their age, we can know any number of things. And then we track them over time, whether that's minutes, hours, days, weeks, years. It all depends on the study, right? Then we have whether or not the event occurs. So in this case, this person may have died, whereas this person here was still alive by the time the study ended. So they were censored, is the term we use, right? But again, we need to have known individuals tracked over time and have a time and then an event that we're tracking. Okay, so again, it's really just how long until an event happens. This doesn't have to be death. It can be certainly any other event that we want to track, right? In fact, there's the data tab and the biostat squid tutorials online already that were created by other individuals that are really good, and they give some great examples of some non-survivor or non-sort of medical examples of survival analysis, right? Within that, we're going to talk about three specific methods. Again, there's more methods out there than this, but these are the three that we'll focus on. So the first will be the Kaplan-Meier curve. And this is really just drawing the curves themselves for survivalship, right? So we've got survival rate on the y-axis and time on the x. And so this is really just visualizing the data. Then we can use a log rank test to see if those curves are different between one or more groups, right? So we can test if our curve is different from a presumed distribution, but we can also test if, let's say, our two treatments may be medicated and unmedicated, if their survivalship curves are different. And then finally, we'll talk about Cox regression or Cox hazard proportional regression analysis, which is a long name, right? Cox regression is much shorter. This allows us to take into account multiple factors, so we can have a more complex model to see how survivorship odds might change in relation to multi-covariates, or if we say whether they're medicated or unmedicated, but also their age at diagnosis, right? So we can take into account some continuous covariates or other explanatory variables all at the same time, right? So again, these are the three most common that we see. There's other tutorials out there that are probably certainly better than mine, right? But we're going to try and cover all of these and give you an explanation of what they're doing. So again, Kaplan-Meier survival curves are just used to graphically represent survival rate or survival function, whereas the x-axis is typically time and the y-axis is the probability of survival or survival rate. And we can interpret these curves simply by sort of looking at them and starting to get some estimates of probability or sort of the mean survival time in some cases, right? So we can check the shape of the curve. The steeper the curve, the higher the event rate, right? So if your curve goes down fast, it's likely that survival is shorter for whatever we're looking at, if we want to use survival as an example. If it's a sort of flatter curve or a lower slope, that's a lower rate of occurrence, right? So here, if we look at these two, here's group 1 in blue, group 2 in red. Group 1 is low risk, so we can see how flat this curve is. Even at 70 months, the survival rate is still almost 60%. The high risk here, this is a very steep curve, and at 70 months, the survival rate is essentially 10%, right? And then we can get the risk table that's associated with this, so we can see the number of events that occur on each time point in these two groups, right? So again, the curve allows us to visualize the data. We can also then look at sort of survival probabilities at specific times. What's the mean survival rate at 12 months, 24 months, 48 months, right? And then we can also start to look at the sort of the lengths of the horizontal line and sort of the survival duration. So how long would somebody in that particular group likely survive, right? And again, since we're tracking individuals across time, studies have to end at some point. We may have censored data where that individual is still alive at the end of the time point, but that doesn't terminate the interval. Whereas if we have a treatment where all the individuals die before the study dies, that would terminate our curve, right? That interval would not go as far as the study examined. Again, this biostatsquid.com, this individual does a great job and has several sort of blog posts and videos about each one individually and then about them as a whole if you need some supplementary videos to watch. Okay, so we've graphed our survival curves now, and we can again start to describe some survivalship probabilities and look at how those curves differ, but now we actually have to quantify the differences between those two curves, and we do this with the log rank test, right? This is the most common method to quantify differences between two survival groups, and this is going to compare the distributions of time to event in two or more independent groups, right? So again, if we have 4 treatments, we would have 4 lines, and we would look at the differences between those lines. The Kaplan-Meier curves allow us to visualize those differences. The log rank test allows us to statistically say if they're different or not, right? So again, if we have these two separate, if we put them on the same graph here, are the pink and the blue curves the same or not the same? Visually, they look different. We need to know quantitatively, are they statistically different from each other? Okay. So again, the null hypothesis in the log rank test is that both groups have identical distribution curves. The alternative hypothesis is that they both have different. And that's just if there's 2 groups, right? So if there was more than 2 groups, we would say the null hypothesis would be all groups have identical distribution curves. The null hypothesis would be that not all groups have identical distribution curves. This doesn't allow us to say which one's different from which, per se. We can get into that with the Cox regression. But this would just ask if among our groups, if those curves are the same or not. Okay? The log rank test is quite similar to a chi-square test, right? The observed minus the expected squared over the expected. In fact, the test statistic you get with the log rank test will be the chi-square value with its degrees of freedom and associated p-value. Okay. And so again, if we put these two things together, here's the Kaplan-Meier curves for the 2 different sexes, the risk table, and then we can see here an associated p-value. This p-value would be from the log rank test to suggest that these 2 curves are indeed statistically different from each other. The shading across either of these lines is the confidence intervals. Okay. So again, it really can tell us if the 2 curves are different or not, but it doesn't actually provide an estimate of the size of the difference or the effect size. And it really only allows us to look at one variable at a time. And so this is when we need the Cox proportional hazards survival regression, or Cox regression for short, to allow us to look at some more complex models and if survivorship differs within those models. Okay. So again, Cox regression, also known as proportional hazards model, We can analyze survival times of individuals or the time to specific events, but we can incorporate multiple variables along with that. So we can have our grouping variable, right? But we can allow for other covariates like age or size of tumor or the amount of a specific medication given, right? But we can also look at other explanatory factors that are also categorical. And so we can build more complex models that look at multiple variables at a time, and we can actually get an estimate of the effect size or how much survival differs here, right? And so the regression calculates hazard rates, or if we're looking at across multiple levels of a categorical variable, hazards ratios, which is essentially the probability of an event for one group compared to another group, right? Let's say males are 2 times more likely to die within 50 years than females, right? And so that hazard ratio between males and females gives us some insight as to how survivorship might differ between those two groups, right? Again, the inclusion of these other explanatory variables allows us to estimate the effect they have on the probability of the event or the probability of death, right? The main assumption here is that the hazard is constant across time, and we have to look at the residuals in order to do this, and I'll show you how to do that in RStudio. But really, Cox regression assumes that the risk between groups is sort of the same throughout time. So again, the hazard rate here is really just the probability of death, and so the covariates can explain how they influence that hazard function, right? And so maybe if you're, a particular sex, you smoke and you work out, your hazard rate is this, right? If you're the opposite sex, you smoke and you work out, the hazard rate would be this, right? And so it allows us to look at multiple variables and see how they influence the probability of the event. Again, I often say death because survival is the most common, right? And so, again, we can get hazard ratios between groups, and this is what's called a forest plot. And so we can look at how these hazard ratios differ among our explanatory variables. And again, we gain more insights as to not only which groups may be different from which, but also how much these variables affect the survival rate. Okay, and so again, the outputs of a Cox regression are the coefficients. These are what we're going to look at. These are beta coefficients and indicate sort of the log hazard ratio. Okay, assuming we hold all other covariates constant, we can look at that beta. If that's a positive beta, that means an increase or a higher risk. If it's a negative beta or a negative coefficient, that's a lower risk. And then if it's 0, it means there's no difference in the hazard. It doesn't mean there's no risk. It just means there's no difference in that hazard among those groups. Okay? And again, then the hazard ratios, again, this is comparing 2 levels, right? So these are looking at 2 coefficients at once. So it's the relative change in hazard from one unit to another. And again, that can be a covariate like age. So what's the hazard ratio as you get older? Or it could be what's the hazard ratio between males and females. A hazard ratio that's greater than 1 indicates an increased hazard compared to the baseline, right? Less than 1 indicates a decreased hazard, and hazard ratio, I shouldn't say rate, these are all ratios, I apologize. And a hazard ratio of 1 equals no change between the two groups. Okay. So again, Cox regression is going to give us coefficients, which we can interpret, and also hazard ratios. And again, we can use those to gain more insights as to what might influence the time to event among our samples. Okay, so again, I'm going to run through some Roach data that was collected in class, right? So here's our data. We have our cup ID. We have the sex of our dubia roach, male or female. Then we have the treatment, right? Some of them were housed at 26 degrees Celsius, others at 40, and others at 0 degrees Celsius. Again, I have 26C, 0C and 40C, simply so that RStudio knows right away that it's a categorical variable. Time, that's in days, and then status is whether they survived or not, right? Whether the event happened. So in this case, 0 would mean that they were still alive, and 1 is if they died. And in this case, we ran this for 40 days. So these individuals are actually censored where they were still alive at the end of the study. Okay. So we're going to want to open up RStudio. And in this case, we're going to actually need some packages installed. And so we want to install survival, ggservfit, servminer, and actually tidyverse. In order to do that, you can go to Tools, Install Packages. And now, of course, it's going to want to think for a while. And then I can just type in the name of the package here. So survival. It actually starts to autofill. I can click on that and then click Install. I've already installed all of these packages, so I'm not going to do that in this video. But we want to install those 4 packages. Okay. Then again, as usual, we want to set our working directory session, set working directory, choose directory, and I'm just going to choose this folder. Okay, so now I've set my working directory. Now I need to actually load those packages. So I called, those are now libraries. So library, open parentheses, the name of the package, close parentheses. So here I'm going to load tidyverse, survival, ggservfit, and servminer. Okay, and then we can see in the console below, it might take a little bit to load those, but now I go back to my little prompt, and I know all 4 of those are loaded. Now I'm going to upload the data. So again, I'm going to call the data Roach. So as I refer to Roach from here on out, this is referring to the data set. Assign to, right, read.csv, and then in parentheses the name of the file. This is just roach survival.csv. And I can see that Roach now pops up in my environment. I have 46 observations of 5 variables, right? I can look at the headers for that. So if I type head Roach, that starts to spit out the first few observations of each. Or if I just want to check my variable names, all names, which is column names, again, Roach. And that will give me the names of the variables in this data set. Let me maybe increase my magnification there, right? So here we just have loaded the data set, right? So we downloaded these packages, set our working directory, loaded the libraries for those packages that we installed. You don't have to install the packages every time. Once they're installed, they're installed. You may want to check for updates from time to time, but you do need to load those libraries every time you want to use them. Okay? So renew session, you need to load those libraries. Then I imported the data set and I explored the data set. Okay? So again, I have ID, sex, treatment, time, and status. Notice that they're all begin with a capital letter. And so remember that I have to type things in exactly as they are. Otherwise, RStudio will not recognize them. If you don't have your data in 1s and 0s, there's ways to do that. So here I can check unique. Then Roach is the data set, $, status is the variable. So that's going to give me all the unique values in that variable in my data set. It's just 0s and 1s. I'm okay. If it was dead and alive and I wanted to change it to 0 and 1s, which you would probably need to for the analysis, there's ways to do that in R that I won't cover at this time. Now we can take a quick look at how many of our roaches live versus died by this table function, right? So table Roach $ status. Okay, so we had 27 that were alive, 19 that died. Again, if I wanted to see how many were in each treatment, I can do table Roach $, in this case, treatment. Close those parentheses. Oops, run that. 13, 16, and 17. Those are my sample sizes in my 3 treatments. Okay. First thing I need to do is create what's called a survival object. Okay. So this will be the object that we use in not only the Kaplan-Meier, but also the log rank test. Okay, so I'm going to call it serve underscore object because it's just a survival object assigned to serve is the function. Okay, open parentheses time equals, again, Roach is a data set, $sign tells it what variable to look at, and then we actually have a variable called time. So we're going to use time with a capital T, comma, event, because again, we're looking at time to event, so we're trying to create an object that denotes which variables we're looking at, which one's associated with our time or our length, and which one's associated with our event. So event equals Roach $sign status. Okay, I'm going to run that. Okay, now I have this, right? And so I can look at this vector here, head serve object, okay, and that's going to spit that vector out for me, or part of that vector. Okay. Now we can use that survival object to create our visualization. Okay. So I'm going to create this object called S1. Again, assigned to serve fit. So now I'm going to fit a model, parentheses, serve object. That's what I just created, that vector tilde 1. Okay, that tilde is sort of next to the, so if I hit shift and then the button next to 1 on my keyboard, you should find that little tilde, right? So that's my object, and the data is Roach, okay? And so now I'm going to create another set of data that's a list of 16, that's S1, and if I look at the summary for that, now again, I can see here's my time, here's my event, and the risk and the survival, the standard error, and my confidence interval. Okay? And every time that there's a death, you notice the 40s don't appear here. These are really just the deaths. Okay. I've created that model now. So now the Kaplan-Meier plots can be created using that. At first, I'm just going to do the overall survival, and then I'm going to look at the Kaplan-Meier curves with the 3 lines. So I'm going to create KM curve here. So KM underscore curve, that's just what I'm going to name it. You can name it whatever you want to. Assign GG serve fit is the function, open parentheses, S1. Okay. That's this is what I'm going to plot. Okay. Line width equals 1. Again, I can change this. If I want a thicker line, I can go up or I can go down. Plus, now my labels, labs, open parentheses, X equals time in days, comma, Y equals overall survival, close parentheses. Okay, that creates my curve, and there's my curve. So if I zoom out here, there's my Kaplan-Meier curve right there. Now this is across all groups. Okay, so this is ignoring treatment and just looking at survival across time. So again, here's overall survival, that would be 100%. And we notice that even at 40 days, we're still about 58% of them are alive because we didn't have that many roaches die in this experiment, right? Okay. So again, that's looking at overall survival. We want to now look at those survival curves for our individual treatments. Did the temperature treatment for our roaches affect survival? That's what we're most interested in. So now we have to sort of lump in our categorical variable. And again, we can just do table roach treatment to see, again, how many should be in each. Now we can use our original serve object. I'm going to create a new model. So here's S2, assigned to serve fit. Now it's serve object. Instead of tilde 1, meaning that I just wanted to graph all the data, now that's basically saying that my survival by treatment. Okay. So I have my treatment variable in there, comma, data equals roach. Okay? And now I have S2, a list of 17. Now I'm going to plot that again. Okay? And again, I could create a second object here. I don't want to do that. So KM2 equals GG survive or serve plot. Now S2, because I'm using this new model that incorporates treatment. Data equals Roach. Again, size equals 1. Now because I have different treatments, I want those curves to be different colors. So palette equals C for concatenate. And then I'm just going to blue, gold, and red. Again, this should be in alphabetical order, right? Sensor shape equals a vertical line. So when a individual is censored in this project, it should be represented by this vertical line. We didn't lose any roaches to censorship during our 40 days, but again, we ended at 40 days. So we shouldn't see a lot of these lines here. Okay. And then what size we want that line to be is 4. Confidence, so conf dot int, right? That's my confidence interval. Do I want to show those? I have equal true. If I change true to false, it's just going to be the lines. I'm going to do it both ways to show you the difference. Eval equals true. This is actually going to give us the log odds or the log rank, but we're going to do the log rank separately in a little bit. Risk to dot table equals true. Do I want to show the risk table underneath? Again, true. I can change that to false, right? And then I can change the strata. I can change the height. I can do lots of other things if I want to. This, if you went to, if I did question sign GG serve plot. This is going to be the help function. And so over here in help, it's going to say drawing survival curves using ggplot2. It's going to tell you all about that function, and look at all of these things that I can manipulate. Again, ggplot2, very powerful, can really manipulate the visualizations. I'm just going to show you a small portion of that. Okay. And this is ggplot theme. Theme equals black and white. I've already said what color lines it can do. Again, you can tinker around with all these other things, but I'm really just going to show you the basics. Okay. So I'm going to run that. I can see that it created it. Now I can just say cam _2 and boom. Here is my next plot here. So here blue treatment is 0, gold is 26, red is 40C, again in alphabetical order. So I choose blue is normally cold, gold would be normal, and then red the hot roaches, right? And then here's my risk table. So number at risk in my timelines, okay, across my treatments, and they're stratified. This seems kind of busy with the confidence interval. See the shading here? And now here's my associated p-value, p equals 0.47, which is pretty obvious given how much the confidence intervals overlap. I'm going to do the same curve, but turn off the confidence intervals. Let's zoom back out or zoom back in. Here's the same curve. Again, here's my line at 40 because that's when we stopped the study. That's when some individuals were censored. And now we can see just the lines without the confidence interval shading. Everything else should be the same. It just helps make it not so busy. Whether you want the confidence intervals on there or not is up to you. Again, visualization should be, in my opinion, simple and clean to best explain data to the reader, right? If confidence intervals helped explain that, we should certainly include those. Okay, so again, we have a p-value here, and that p-value really is associated with the log rank test, but we haven't actually officially done the log rank test. Okay, so I'm going to do that now. So log rank res _ treatment, it's the object assigned to. Serve diff is the function. Open parentheses, serve time, comma, status. So this is basically the time in the event. Tilde treatment. Okay, so I want to look at differences among treatment. Data equals Roach, right? And so I'm going to create that object, and now I'm going to spit that back out. So here are all my treatments, my sample size 13, 16, 17, the observed events 6, 5, and 8, expected number of events 4.6, 7.56, 6.75, observed minus expected squared divided by expected, right? And here's my chi-square of 1.5 with 2 degrees of freedom and a p-value of 0.5. Now the Kaplan-Meier had 0.47. This is 0.5. Same, right? So now I have my Kaplan-Meier curve with my 2 treatments and my log rank test saying that the survival curves of those, 3 treatments, do not differ. Okay? So as it looks right now in our data set, the temperature that the roaches are exposed to did not affect their survival over the course of 40 days. I could be done there, right? But we also looked at male and female roaches. And so what if survivalship wasn't equal across the 2 sexes in regards to the treatment? Okay. So now I want to take a look at 2 variables at the same time. Log rank and Kaplan really only look at one at a time. I could go back and create Kaplan-Meier curves for the sexes, right? I could go back and do the log rank test for the sexes. I could create a new variable that is the treatment by sex combination. But the easiest thing to do is just to do a Cox regression analysis. So I'm going to create a new object called Cox underscore res, assign to Cox pH. That's Cox proportional hazard. From parentheses, serve, again, time, comma, status, tilde, treatment. Now I'm going to add in sex. So plus sex, comma, data equals Roach. I'm going to run that. Now I've got a new object over here. And I can spit this out. Here's my coefficient. Here's my exponent coefficient, the standard error of the coefficient, the z-score, and the p-value for each of those coefficients. Okay. I can also get the likelihood ratio test on 3 degrees of freedom and an overall p-value. Okay. I can do a summary of that, right? Here's my Wald's test, my likelihood ratio test, and my log rank test, all on 3 degrees of freedom and all of p-values of 0.7. Okay. Again, suggesting that if I take it into account treatment or sex, there's no difference. Now, notice here I used plus. This is asking them to take those into consideration separately. What about the interaction between sex and treatment, right? So what if males and females didn't respond the same way across treatments? I can use this, my multiple sign or my asterisk over on my numeral keyboard here. So treatment times sex, this is going to do the interaction. So again, I'm going to create an object this time called Cox underscore res1, assign to Cox pH. Same thing, I just changed a plus sign to a multiple sign. Now I'm going to run that. Now here I have interaction terms. Okay. So I can see the coefficients, the z-scores, and the p-values for all those. I can do the summary for my new model. Again, still not significantly different, but it's fine. Okay. We can see that these hazard ratios do not significantly differ from 1, or these hazard rates don't significantly differ from 1. Okay. And so there doesn't appear to be any effect of sex or treatment in our data, which is fine, right? But we can start to take a closer look at it, right? First off, we want to check to see if we meet the assumptions of the Cox regression. So I'm going to test my assumptions. So I'm going to go test, assign to survival, : Cox.z pH, and then my model, Cox res. Okay. And here you can see the chi-square and the p-values for each one of those. Now I can plot the Schofield residuals over time to see if I am violating the assumptions. So that's serve minor, : GG Cox Z pH of the test that I just created. point size 0.1. And let's look at those. Oh, excuse me. We get a p-value for each one of our variables, right? So here's treatment. The p-value is 0.1176 and sex 0.6113. We really would like these to be in a straight line, and these little plots here, we actually could probably make those a little larger. Let's try this again with bigger dots there. We would really like to see these linear and uniform, but these large p-values are telling us that our hazard rates do not significantly change over time, which is good, right? Because that's the big assumption there. And so we've done our Kaplan-Meier, we did our log rank test, we didn't find any difference in survival among our treatments. We did a Cox regression to see if sex had any effect there. It has not. We tested our assumptions. The next thing we could do is do a forest plot. So GG forest, and then open parentheses Cox res, so our first Cox regression, comma, data equals Roach. And let me zoom in on this one for you. Here's now our hazard ratios. So treatment, 0 is the reference, and there's our other 2. And sex female is the reference, and there's our male, right? So since this is our reference, you notice that it's right on 1. Here, 26C, again, that's less than 1. We can see there's a slightly less chance of dying when you're in 26C. Look how big the confidence interval is there. It doesn't significantly differ. Right, here's 40C, again, slightly less, but again, large confidence interval. Here's our reference for sex. There's female. Males actually have a slightly higher chance of dying, but again, a very large confidence interval on those hazard ratios. So again, it turns out that we didn't find any significant relationships in our Roach data, and we can do this for our other model where we use the interaction instead of them separately, but we're going to get sort of the same thing here. Okay, except now we have the interaction term figured in there. So no significant effects of treatment or sex on Roach survival, but it shows us how to go through and look at survival data. So as long as we can follow individuals across time, so we know the time, we know the event, in this case whether they lived or died, and then we have our other explanatory variables, treatment, sex, age, the amount of a substance you gave them, right? Then we can see how those things affect survival by going through survival time analysis. Okay, that is it for this tutorial.